Hey folks, my name is Nathan Johnston. Welcome to Lecture 39 of Introductory Linear Algebra. In today's class, I want to make explicit something that we've talked about implicitly a little bit over the last couple of lecture videos. So I'm going to scroll back up to something that we saw in the previous video. When you compute the eigenvalues of a matrix, what do? You set determinants of a minus lambda I equal to 0. Okay, and this equation here, it's very, very special. It turns out it's always a polynomial equation, okay? It's always something like this. Here we've got lambda squared equals minus 1. This is a polynomial equation, right? This is a polynomial in lambda that we're trying to set equal to something. Okay, and furthermore, its degree is 2. Its degree in this case is the size of the matrix. The matrix is 2 by 2. The degree of this polynomial equation is 2. Okay, and that's not a coincidence. This always happens. Okay, so this polynomial is something that we call the characteristic polynomial. This determinant of a minus lambda I is the characteristic polynomial. And the equation, determinant of a minus lambda I equals 0, that's the characteristic equation. Okay, and the reason that it's always a polynomial of degree n is, well, suppose they've got an n by n matrix. You're computing determinant of this thing here, and remember from last week, we have explicit formulas for this determinant. Okay, and if you use those explicit formulas, you always get exactly this polynomial that we're talking about. Because, well, think about how these explicit formulas are constructed. They're constructed from cofactor expansions. And when you construct something out of cofactor expansions like this, if the matrix is n by n, what you're doing is you're adding up and subtracting a whole bunch of terms, and each one of those terms is a product of n entries of a minus lambda I. Okay? And if you're multiplying together n entries from a minus lambda I, well, each of those things that you're going to multiply together has either 0 or 1 lambdas in it. So when you multiply together n of them, they have at most n lambdas in it. So it's going to be a polynomial of degree less than or equal to n. And furthermore, on the diagonal, you have exactly n lambdas. Okay, and that term, when you multiply together all the diagonal entries, that is one of the terms in the determinant, okay, in these cofactor expansions. Okay, so this thing here, it really is, it's always a polynomial in lambda, and it always has degree exactly equal to n, the size of the matrix. Okay, and this observation is useful because we know lots of things about polynomials. So now that we know we get eigenvalues from polynomials, well, right away we're going to know lots of things about eigenvalues as well. So for example, we know that every degree n polynomial has at most n distinct roots, which immediately tells us, if we just string these facts together, that if you have an n by n matrix, it has at most n eigenvalues, okay? An n by n matrix, like a 2 by 2 matrix, is never going to have 3 eigenvalues. It's never going to have 4 eigenvalues. It'll either have 0, 1, or 2, always, okay? Because we know that these eigenvalues, they come from a polynomial equation of degree 2. All right, so let's go through another example of computing eigenvalues and eigenvectors now that we have this in mind, now that we understand eigenvalues a little bit better, okay? So here we've got a 3 by 3 matrix. Okay, so we know right away we're going to find at most 3 eigenvalues. All right, let's actually find them. Okay, so step 1, find the eigenvalues, then we'll do eigenvectors later. So to find eigenvalues, set determinant of a minus lambda I equal to 0, which just means you take this matrix, subtract lambda off of the diagonal. Okay, then we use our explicit formulas for the determinant to expand out that determinant there, right? So it's going to be the product of the forward diagonal, which is this first term here, then the product of the next wrapping around forward diagonal, which is this plus 1, and the next wrapping around forward diagonal is the minus 2, and then the 3 backward diagonals as well, also wrapping around. Okay, and those gives us those 3 negative terms there. Okay, now remember our goal is to get this polynomial completely factored so that we can see what its roots are, because those roots are the eigenvalues. So what I'm going to do first is I'm going to simplify these terms over here. Okay, I got 2 times something minus that thing, so I'm going to start off by, canceling out the extra multiple there, so that I've just got a single 2 minus lambda. Okay, and when that simplifies down, it simplifies to this. Notice that I've combined these 2 terms here into a 2 minus lambda squared. Okay, and now if you look at these terms over here really carefully, you'll notice that actually every single one of them cancels out with each other. We've got a negative lambda, and we've got a plus negative lambda. Okay, we've got a minus 1, plus 2. Those all cancel out with each other, and you're just left with this first term here, okay, which is already factored. It saved us the trouble of having to factor anything just by noticing that everything over here canceled out with itself. Okay, so then this is the characteristic polynomial, and furthermore, it's the factored form of the characteristic polynomial that makes it easy to see what the eigenvalues are. So the eigenvalues are just the roots. In other words, the eigenvalues are 1 and 2. Okay, so those are the only eigenvalues of the matrix. And I mean, this is consistent with what we said before. It's a 3 by 3 matrix. It has at most 3 eigenvalues. Okay, here it has 2 eigenvalues, 2 distinct eigenvalues. Okay, great. So we know the eigenvalues of the matrix, 1 and 2. We know the characteristic polynomial of the matrix. So all that's left is find the eigenvectors of the matrix. And in particular, we're going to find bases of the eigenspaces of the matrix. Okay, so what do? Well, we set up the linear system that we always set up to find eigenvectors. Okay, you start off with one eigenvalue at a time. So lambda equals 1 is as good a starting point as any. And you subtract lambda off of the diagonal of A. So we're going to subtract 1 from the diagonal entries. So 1's going to become 0, 2 will become 1, and 2 will become 1, and we get 0, 1, 1 down the diagonal now. Okay, so this is a minus lambda I, and augment with zeros on the right-hand side. That's the linear system that you solve to find eigenvectors. Okay, and then just go ahead and solve that linear system. Okay, do Gauss-Jordan elimination, bring it all the way down to reduced row echelon form, and you're going to get this. So I've skipped over the row operations. You can try that on your own. You know how to solve linear systems at this point. Okay, and now we look at this reduced row echelon form, and we see, there's a leading entry in that first column, there's a leading entry in that second column, but there's no leading entry in the third column. So that means v1 and v2, the first 2 entries of the eigenvectors, those are leading, whereas v3, the third entry of that eigenvector, it's free. It can be anything it wants to be. Okay, so v1, v2 are leading, but v3 is free. Okay? And then what we can do is we can look at this reduced row echelon form and figure out what those entries of the eigenvector have to be as well. Okay, so I'm going to scroll back up here just a little bit. If we look at this first row, remember that's an equation, and what this tells us is 1 times v1 plus 0v2 plus 0v3 equals 0. Okay, so that's v1 equals 0. The second equation tells us 0v1 plus v2 plus v3 equals 0. So that's our second equation. And for any equation involving a free variable, just rearrange it so that's leading variable in terms of the free variables. Okay, so rearrange this equation to get v2 equals minus v3. Okay, and then you can stick this into vector form. Okay, you just say, hey, v1, v2, v3, what does that equal? Well, what was v1 equal? It equals 0, so I put that in the first slot. And then what does v2 equal? Well, it equals minus v3, so I put that in the second slot. And then what does v3 equal? Well, v3 is free, so it just equals itself. It can be anything it wants to be. Okay, and then as always with these eigenvector calculations, you can pull the free variables out at the end of the day, pull the v3 out in this case, and you're going to get 0, minus 1, and 1 left over. So all of your eigenvectors corresponding to lambda equals 1 are multiples of this vector here, 0, minus 1, 1. So in other words, this vector 0, minus 1, 1 forms a basis of that one-dimensional eigenspace. All right, let's do the same thing for the other eigenvalue, lambda equals 2. So this time we've subtracted 2 off of the diagonal of A. So the diagonal used to be, like for A itself, it was 2, 1, 1. Well, subtract 2 off of each of those, and now the diagonal is minus 1, 0, 0. And again, you do your row reduction magic, bring that all the way down to reduced row echelon form, and you get this matrix over here. And we see something very similar happens here to what happened on the previous page. First 2 columns each have a leading entry, so v1 and v2 are leading. Third column has no leading entry. Okay, so the third variable, v3, the third entry in your eigenvector, is free. Okay, it can be anything it wants to be. Okay, so v1, v2 are leading, v3 is free because there's no leading entry in that third column. Okay, and then just write down what these equations mean. Okay, this tells us that v1 plus a half v3 equals 0, and rearrange that so that it's leading variable in terms of free variables. Okay, so leading equals something involving free. Okay, and similarly, the second row, that tells us 1v2 plus 1/2 of v3 equals 0. We'll just rearrange so that the leading variables on one side of the equation, free variables are all on the other side of the equation, and you just get this. Bring the 1/2 v3 over to the right-hand side. Okay, and then what's that tell you? Well, if you put it in vector form, it tells us that v1, v2, v3 equals, well, was v1 equal? It equals minus a half v3. Was v2 equal? It equals minus a half v3. And what's v3 equal? It's free. It just equals itself. And then you can factor the v3 out of everything, and you're left with, well, the eigenvectors, they're multiples of minus a half, 1. In other words, the single vector here, again, it forms an a basis of the eigenspace, of that one-dimensional eigenspace even. Okay. So I want to try to unpack a couple things that occurred in this example here. Okay, we had a 3 by 3 matrix that only had two distinct eigenvalues. Okay, so it had the eigenvalue 1 and it had the eigenvalue 2. But this eigenvalue 2, in a sense, it occurred twice, right? This characteristic polynomial, here is lambda 1 as a root, here is lambda equals 2 as a root, but it occurs again, right? In other words, if you sort of write out this polynomial sort of in long form, instead of using squared up here, you just write out each linear term multiplied by each other linear term, you get this expression up here, 1 minus lambda times 2 minus lambda times 2 minus lambda. And you can see that 2 minus lambda is occurring twice. In other words, lambda equals 2 is sort of occurring twice as an eigenvalue. Okay, and we give a name to this idea of an eigenvalue occurring multiple times as a root of the characteristic polynomial. In other words, this idea of an eigenvalue occurring multiple times as an eigenvalue of a matrix. We call it the multiplicity of that eigenvalue. Okay, and in particular, occurring multiple times as a root of the characteristic polynomial, we call that the algebraic multiplicity of that eigenvalue. Okay, so the algebraic multiplicity of an eigenvalue lambda, it's just the multiplicity of lambda as a root of the characteristic polynomial. In other words, it's the number of times it occurs as a root of that characteristic polynomial. It's the number of times that that linear factor occurs as a factor if you completely factor that polynomial. How many times does lambda minus that particular eigenvalue occur as a factor there? Okay, what is the exponent of that factor? That's the algebraic multiplicity. Okay, there's another slightly different notion of multiplicity as well, though. Okay, we call the geometric multiplicity. Well, that's the dimension of the eigenspace associated with that eigenvalue. Okay, so if I just scroll back up to this example that we just went through, okay, for lambda equals 1, to compute what the geometric multiplicity of lambda equals 1 is, we just look at this basis of the eigenspace corresponding to lambda equals 1. And we see, well, how many vectors are in that basis? Well, there's exactly one vector in that basis. So that eigenspace is one-dimensional. Geometric multiplicity is 1. Okay, similarly, for lambda equals 2, well, here's the basis of the corresponding eigenspace. It only has one vector, so that eigenspace is one-dimensional. So the geometric multiplicity of lambda equals 2 is also 1. Okay, so let's write this all down. Okay, in the previous example, so this matrix that we talked about the eigenvalues of just a second ago, the eigenvalues were lambda equals 1 and lambda equals 2. For lambda equals 1, the algebraic multiplicity was 1, because the lambda minus 1 term, well, that only occurred as a factor in the characteristic polynomial just once. Lambda equals 1 was just a root once. And the geometric multiplicity was also 1, okay, because the eigenspace was one-dimensional. For lambda equals 2, so like every different eigenvalue gets its own algebraic multiplicity and geometric multiplicity. For lambda equals 2, the algebraic multiplicity this time was 2, because remember, lambda equals 2 or 2 minus lambda, that occurred as a factor in the characteristic polynomial twice. The exponent on it was 2. Okay, so the algebraic multiplicity was 2. The geometric multiplicity was still 1, because its eigenspace was still one-dimensional. Okay, I want to go back and contrast this example with an example that we saw a few pages ago, back on page 5 of this week's notes. This was an example that we went through 2 lecture videos ago. We computed the eigenvalues of this 3 by 3 matrix, as well as bases of the corresponding eigenspaces of this matrix. Okay, and we computed that the eigenvalues were lambda equals 1 and lambda equals 2, just like the example that we went through in today's video. Okay, and furthermore, the algebraic multiplicities were even the same. Okay, lambda equals 1 with algebraic multiplicity 1, and then lambda equals 2 with algebraic multiplicity 2, because the lambda minus 2 factor occurs twice here. Okay, but the geometric multiplicities are different. Okay, for lambda equals 2, in the example that we went through in today's class, we found the geometric multiplicity was just 1. But in this example that we saw a few pages ago, the geometric multiplicity was 2, because there are 2 vectors in this basis of the eigenspace. So the eigenspace in this case was 2-dimensional. Okay, so the geometric multiplicity is 2. For lambda equals 2. For lambda equals 1, the geometric multiplicity was still just 1, because there's only one vector in that basis there. So the eigenspace is one-dimensional. Okay, so this maybe slightly hints at a possible theorem here, okay? If we sort of catalog what we've learned so far and sort of the examples that we've gone through, we've seen that, hey, here's a 3 by 3 matrix where the algebraic multiplicities are 1 and 2, and the geometric multiplicities are 1 and 1. And we've also seen an example where the algebraic multiplicities are 1 and 2, and the geometric multiplicities are 1 and 2. Okay, and in every single one of those cases, geometric multiplicity isn't necessarily equal to the algebraic multiplicity, but it is always less than or equal to the algebraic multiplicity. Okay, and that is true. That's true in general for every single matrix. Okay, so if you've got any old square matrix, then for every single eigenvalue of that matrix, the geometric multiplicity is going to be less than or equal to the corresponding algebraic multiplicity. Okay, so the fact that, hey, this 1 is less than or equal to 1, not a coincidence. The fact that this 1 is less than or equal to 2, not a coincidence. Okay, so this is a theorem. It's proved in the textbook. I apologize. We're going to skip over the proof just for time reasons. There are some things that I really want to get to at the end of this week and going into next week, and we're just running out of time to do it. Okay, there's one final polynomial related fact that I want to talk about. And this fact, it's going to tell us a little bit more about how eigenvalues work, and in particular, how the algebraic multiplicity of eigenvalues work. Okay, the result is called the Fundamental Theorem of Algebra. Okay, so it's a result from complex analysis, so maybe you've seen it, maybe you haven't. But what it says is if you have any degree n polynomial, so the highest order term is lambda to the power n, well, what it says is then that polynomial, it has exactly n roots, okay? As long as you do two things. As long as you allow complex numbers, okay? Like your roots can be complex numbers even if the coefficients are real. And the other thing you've got to do is you've got to count the roots according to multiplicity, okay? So the way that you count the roots is like you add up the exponents in the linear factors of the fully factored form of that polynomial, okay? So you're sort of counting how many times that root occurs, okay? So we're not saying that there are exactly n distinct roots, like roots can occur multiple times, it's just you're counting up how many times they occur. And if you add up all of those, hey, how many times does this one occur? And how many times does this one occur? And so on, then you get exactly n. You get exactly the degree of the polynomial. Okay, and if you apply this result to the characteristic polynomial, then you get a statement about eigenvalues and algebraic multiplicities. And what that statement is that, well, if you allow complex eigenvalues, then the sum of the algebraic multiplicities of the eigenvalues of any n by n matrix is exactly n. Okay, so if you take any matrix, you compute its eigenvalues, keeping in mind that we're allowing complex eigenvalues, and then you compute the algebraic multiplicity of each of those eigenvalues, and then you add up those algebraic multiplicities, what you will get is n. You will get the size of the matrix that you started with. Okay, and if you combine this with this previous theorem, geometric multiplicity is less than or equal to algebraic multiplicity, well, we're going to find something analogous, but a little bit weaker for geometric multiplicities. If you add up the geometric multiplicities, you might get n, but you might get something smaller as well, okay? You don't necessarily get n if you add up the geometric multiplicities. Okay, so let's just go back and remind ourselves of how this works for all of the examples that we've gone through this week. Okay, so all the matrices that we've seen eigenvalues and eigenvectors for. Okay, for the matrix, the diagonal matrix that has 1/3 and 2 on the diagonal, well, this matrix, the eigenvalues are exactly the 1/3 and the 2. Okay, we talked about how this matrix just stretches the standard basis vectors. Well, those are the corresponding eigenvectors. Okay, that's just a calculation to show that these eigenvalues each have algebraic multiplicity and geometric multiplicity equal to 1. Okay, so if I add up algebraic multiplicity is 1 plus algebraic multiplicity is 1, I get a total of 2, which, yeah, that's the size of the matrix. The matrix is 2 by 2. Okay, here's another 2 by 2 example that we looked at. This matrix 2, 1, 1, 2. We talked about how lambda equals 3 is one of its eigenvalues. It turns out the other eigenvalue is lambda equals -1. We didn't go through that calculation, but it's something that you can check now if you want to. Okay, and also it's just a calculation to show that the algebraic multiplicity of each of these eigenvalues is 1. So again, we see that, hey, 1 plus 1 equals 2, the size of the matrix. Sum of the algebraic multiplicities really is 2. It's the size of the matrix. Geometric multiplicities are also 1 in this case. All right, another 2 by 2 example. This matrix 1, 2, 5, 4, we found the eigenvalues, which were 6 and -1, and exact same thing happened in this case. Algebraic and geometric multiplicities were both 1. You add them up, you get a total of 2, the size of the matrix. For this matrix here, our example of a matrix that does not have real eigenvalues, so 0, -1, 1, 0, we found that the eigenvalues of this guy were complex, okay? They were I and -I, and again, they each had algebraic and geometric multiplicity equal to 1. You add up those algebraic multiplicities, you get 2, the size of the matrix. All right, and we also went through this 3 by 3 matrix a little while ago, okay? And we found that, hey, this guy has 2 different eigenvalues. One of them is lambda equals 2, and for this one, we found the algebraic multiplicity and the geometric multiplicity both equaled 2. And the eigenvalue lambda equals 1, it had algebraic and geometric multiplicity equal to 1. Okay, and if you add up the algebraic multiplicities, you do 2 plus 1, wouldn't you know it, you get 3. You get the size of the matrix. Okay, and that always, always, always happens as long as you allow complex eigenvalues and as long as you sum up algebraic multiplicities. Okay, the sum of the geometric multiplicities might be smaller, right? We saw an example of that too. Okay, that was the 3 by 3 example that we went through today. In the example that we went through today, we had geometric multiplicity 1 and geometric multiplicity 1. You add them up, you get 2. But it was a 3 by 3 matrix. Okay, so the geometric multiplicities might add to something smaller than the size of the matrix. It's only the algebraic multiplicities that always add up to n. Alrighty, so that does it for facts about polynomials and characteristic equations. Let's go on to one final sort of special case about eigenvalues that is a little bit easier to deal with. So this sort of special case that's nice to point out just because it's going to make our life easier in a lot of cases. So let's think about how could we compute the eigenvalues of this matrix here. Okay, so it's an upper triangular matrix. It's 1, 2, 3, but then zeros down here, and then 4, 5, and 6. Okay, let's compute the eigenvalues of that matrix and see something that happens. And what happens is really, really nice. So how do we compute the eigenvalues of that matrix? We compute determinant of A minus lambda I, set it equal to 0. Okay, so that means we're subtracting lambda off the diagonal, computing the determinants of that thing, and we use one of our explicit formulas, right? It's a 3 by 3 matrix, so I know how to compute that. It's forward diagonal plus next forward diagonal, oh, but it has a 0 in it, so that's a 0. And then plus next forward diagonal, which has a 0 in it, so that's a 0. And all of the backward diagonals have zeros in them, right? They all hit at least one of these zeros in the bottom left corner. So the only term in this explicit formula that does not die off because of a 0 is the one coming from the main diagonal. Okay, so our characteristic polynomial, we don't need to do any work whatsoever to factor it. It's already factored for us. So we can see right away, hey, what are the roots of that polynomial? Well, they're just 1 and 4 and 6. So those are the eigenvalues of the matrix. Okay, and if you squint really hard at that, you're going to notice that, hey, 1, 4, and 6, those are exactly the diagonal entries there, right? That's not a coincidence, okay? That always, always happens as long as your matrix is triangular, either upper triangular or lower triangular. Then the eigenvalues of your matrix, easy, easy, easy to find out. They're just the diagonal entries, okay? The eigenvectors, though, don't expect a nice rule for those. The eigenvectors still might be ugly, okay? So we're just going to state this as a theorem, okay, because it's going to be useful for us going forward, okay? So if you have a triangular matrix, so upper triangular, like in this example, or lower triangular is also fine, then its eigenvalues are going to be exactly its diagonal entries. So A11, A22, up to ANN. Always, always, always. And where's that come from? Well, it comes from the fact that, well, I mean, the determinants of a triangular matrix is just the product of the diagonal entries, right? That's a theorem that we saw last week. Okay, so how do you compute eigenvalues? Well, you compute this determinants, and it's just going to be the product of the diagonal entries, 1 minus lambda times 4 minus lambda times 6 minus lambda. And because that's always already factored for us, we can just eyeball what the eigenvalues are. They're just, you know, these entries. All right, and that's all there is to it. Alrighty, so that'll do it for eigenvalues and eigenvectors. I will see you next week when we start doing really neat things with eigenvalues and eigenvectors. In particular, next week we're going to do something called diagonalization, which is as close to magic as math can get. Okay, so I look forward to seeing you then.